Hello and welcome to my Data Tools class. This is a very first lecture introduction. There are 6 other ones that I'm going to produce. The next one will be on reproducible research. So basically learning about R Markdown, which is an awesome tool that lets you create reports using R. And we're going to use that in order to learn about a couple of other features as well. So that's why it's already the second lecture. Then we learn more about data organization and obtaining data from various sources, visualizing data, applying some simple models, and then some advanced issues with R. Our official textbook would be R4DS, R for Data Science, and they also have an awesome website that you can go to. And for the assigned readings for this class, I'm going to basically refer you to that website, r4ds.hat.co.nz. If you want to check out other sources, well, we're also going to make use of some data camp lectures that I'm going to refer to. I also put up this cheat sheets here and a link to the Tidyverse, which is going to be a collection of packages that we're going to rely on for quite a bit. Also, if you're interested in more readings and applied ones to your discipline, check out the Use R series from Springer. So I have an example here for a marketing R textbook that is actually fairly well received. This class will rely a lot on teamwork, and I would assign assignments in pairs, and so you can help out each other. So what is this particular class about? So I have like 11 chapters, and you can click on each of those chapters to skip ahead. And the first one will be to define the goals, and the last one will be on data exploration. So let's get started and talk a little bit about the goals for this class. So what is this class supposed to do? Well, it's supposed to help you to learn to perform data analysis independently, to import and manage structured and unstructured data, to manipulate it, transform it, and summarize it, understand different data sources and also bring them together, then find out how to methodically explore and visualize your data, and to understand some basic functions and how they're written, because you will rely on a lot of functions. So a basic understanding of how that works is probably also going to be helpful. To put simply, you're about to learn about the steps that you need to actually apply the entire data journey within just R. And that makes it a very stable and very error-proof. So what is the data journey? So it's the entire journey from importing raw data to having the communicable results. On the way there, you need to tidy your data, right? You need to do some data cleaning. You may need to do some transformations, and then you visualize your data, develop some models, and probably engage in an iterative process to find the optimal model, and then you report results. All of that can be done with one single integrated script, and it can be turned into a report using R Markdown, which is again the topic of the next lecture. How do you install R? Please also watch my dedicated video on the R installation. Just a couple of things to know. This course will rely on R in combination with RStudio. It's very easy to install on Linux. You just use your package manager. On Windows, you just install R and RStudio. Additionally, I do recommend to install R Tools, which lets you compile code, and that's quite useful if you want to install a package from GitHub. If you use OS X, there's an additional step. You need to install Xquartz. Quartz used to be a feature that was part of OS X. At some point they ripped it out, and so you need to put it back in. But downloading and installing it should be fairly simple. There's 2 more things that you need to do if you want to be able to compile packages, and that's something you need to be able to if you want to install packages from GitHub. You need GCC and gfortran A2. There's a GitHub link where you can download it, and you need to install the command line interface tools. RStudio will probably prompt you and help you to install that. If it doesn't, the simple command xcode select install in a terminal window of OS X will actually help you achieve that. I also put up a link with more details on these compilation tools for OS X. With each new version, there may actually be additional challenges, and usually that website is pretty much up to date on whatever is necessary. So again, we're going to work with RStudio, but there are lots of alternatives in terms of editing our code. You could actually even use a Jupyter notebook, and that would also work. I find RStudio much easier to use if you want to apply this entire data journey and you want to create a report. And also RStudio has lots of integrations with certain packages that make it quite versatile. But again, the choice is yours in general. You could also use Visual Studio, and there's an RTools plugin that lets you actually develop R code. If you already work with Python, PyCharm is probably your editor of choice. It can also work with R code and interface with it. Again, lacking some of the integrations that RStudio has. And then you can use these plain editors like TinR or Notepad++. They're great for editing just a script file, but again, they don't have that type of integration that RStudio can offer. In terms of the different R versions, I do recommend to just install the vanilla R version from Cran, which I've linked to. You may have heard that Microsoft also offers a version of R that's enhanced in certain ways, but it's also usually a version or two behind the official version on Cran. And so if you don't need those particular performance improvement, mostly specific to interfacing with other Microsoft products, then probably the standard R version is the best one to use. We're going to use a couple of packages, and if you just want to install those packages ahead of time, and it's not all of those, but those are like the largest packages that we will be relying on in this course, it's probably a good idea to install them right now so that they are already downloaded and you don't need to wait for them to be installed later on. So a package just needs to be installed once, and then you just need to load that package. Unless, of course, in the meantime, there's a new version that has new features that we want to use. But I think for the purpose of this class, that's probably not the case. So if you just copy and paste this command right here, this install packages, C, Tidyverse, Tidy Models, and so on, that will already download and install those packages on your computer. It may actually take a few minutes. So what is a package actually? So a package is a collection of things, and typically that includes functions, documentation, and sometimes also some data. There are also some packages that only contain data, and that can sometimes also be quite useful. So why is that? Well, a package is a great way to interact with other people, to collaborate, because you probably go through some kind of testing and a process of documentation of your functions or data, and then it's a very convenient way to just pass it on to someone else so they can use it. So there are several packages that already come with base R, so right out of the box, and they implement a lot of standard functions. But of course, it makes sense to install additional packages that give you additional functionality. And that's actually quite useful in software to have things basically in packages, because then the work for development can be split up into different groups, each group working on a particular package and putting all of the efforts into making that package really useful, as opposed to just having one organization managing all the functions within a piece of software. So the official packages are within CRAN, the Comprehensive R Archive Network, and that's sort of the app store of R. There's a review process, so not every package gets accepted onto CRAN right away, and they're going to test, like, does it install in a reproducible manner, and they do some other tests to make sure those packages actually work and are not harmful. So pretty much anything you download from CRAN should be safe. There's also the bioconductor, but it's not relevant for what you want to do here. And then, of course, you can install packages directly from GitHub or Bitbucket. And those are sort of bleeding edge packages that bring maybe new features. Actually, some packages that are available on CRAN are also available on GitHub. And often, there's already a newer version available on GitHub. It's not been verified by the CRAN team yet, but the developers think, well, maybe there's some interesting new functionality in here. And then sometimes you want to decide to actually install the GitHub version because it brings a particular function or improvement that you really need for your project. And again, then you need to be able to compile code. So you need the RTools on the Windows and these the command line interface and the G Fortran if you're using OS X. Okay, let's take a look at the Tidyverse. What is this Tidyverse about? So the Tidyverse really brought a dialect into R. So if you think about R as a programming language, then Tidyverse introduces a little bit of a dialect. So there's a particular way of actually developing your code, and there's also particular style guides of how you're supposed to write your code. And there's a lot of good things about it, and that's why the Tidyverse is actually quite popular. So how does the Tidyverse describe itself? Well, the lead developer says, well, the Tidyverse is an opinionated collection of R packages designed for data science. All packages share an underlying design philosophy, grammar, and data structure. And that's great for coherence. A few examples are packages like readr, which helps you to import data, dplyr, which helps you to manipulate data, tidyr helps you clean data, and ggplot helps you visualize data. There's a lot more packages within the Tidyverse. And again, there's a common philosophy that makes it easy to interact with all of those packages. However, there's some trouble with the Tidyverse. Somebody once asked the lead developer, Hadley Wickham, well, do you expect Tidyverse to be part of base R, standard R? And he then said, well, that's extremely unlikely because the core packages are extremely conservative, so that base R code is stable and backward compatible. I prefer to have a more utopian approach. It can be quite aggressive about making backward incompatible changes while trying to figure out a better API. And maybe you should pause here for a little bit and think about whether that's actually what you want. You want something that's utopian and aggressive? Something that's not conservative and also not stable? Don't we like stability? Don't we want to be backward compatible? And, some people would argue, no, that's not what we want. And we should be really careful about using the Tidyverse. And so Matlov, who wrote this criticism here, he has a lot of admiration for the achievements of the Tidyverse developers. But again, he raises some good points over these issues coming from sort of this very aggressive style of developing something. So if I take R code from 15 years ago, there's a good chance that for the most part it still runs on the most current version of R. Other environments are a bit different. So Python had a drastic change between version 2.7 and 3.7, and they retired the older version. And basically the code is still similar, but pretty much incompatible if you don't want to make a couple of changes. And that's something that R does a little bit different. For the most part, it's backward compatible. There are slight changes every now and then that deprecate certain functions, but overall, it is very conservative. And again, that can be a good thing within an organization. And you just have to know that with the Tidyverse, you have to kind of stay up to date with the latest changes. And that's a little bit of a downside. But then the upside is that you get sort of the latest and best, allegedly, approaches to actually implementing your data journey. Also, to kind of watch out for RStudio, the company. It's a PVC, but still, they're pretty dominant in the R community right now, and that's obviously something to be a little bit careful of. So why do we use the Tidyverse then? I think, as I tried to allude to already, it's pretty dominant actually in the community. It gets the job done, and it's really great and awesome for reproducible research. And it produces easily readable code, which is awesome for teamwork. And that's really the strong point and why so many people like it. Also, the RStudio company, they do a lot to dispel that R versus Python myth. Really, R is an excellent glue language, bringing a lot of different languages together and allowing you to create those reports. And that's really the biggest advantage and the reason why we want to use R in this class. The style guide the Tidyverse put up provides great guidelines. And again, if you keep to those guidelines, I think makes it easier for others, including your future self, to understand what you've just done and to then contribute to it or find mistakes. So let's get started with RStudio. This is what the RStudio window looks like when you first launch it. And so there are certain areas here in the RStudio window that you should look at. So here on the left hand side we have the console. You can also switch to a system terminal or jobs. So console is the R console. That's where you interact directly with R. Terminal lets you pull up the command line or the terminal of your system. And jobs is for managing different tasks that each get their own R instance. That's something we may look at later. We don't really need it for now. And then on the top right part, we have a couple of things that you can display. By default, it shows you the environment, which shows you all the objects in working memory, including data. It gives you a history, so access to the last few commands that you put in, to the console, and connections, which helps you to manage database access. And here on the bottom right, we have files. If you've opened up an RStudio project, it shows you the files within the project. Otherwise, it shows you the files within the working directory that you're working in. You also have access to plots that you produce, and you can go back and forth between plots that you previously have created. You have access to a list of packages that are already installed, and it also lets you install new packages. You have a help file viewer, and you have a viewer that lets you look at HTML output. So some functions produce output that actually comes in an HTML format. And you could view it in a web browser, but you can also put it into the viewer window. On the top left-hand side, we have a button to create a new file or a new project. And on the right-hand side, you have something that lets you load and close projects. So once you create a new file, you see in the top left, it looks a little bit different now, because now you actually have like an editor that lets you edit the script. And then you can actually execute each line of the script and basically run it down there in the terminal area or in the console area. So if you want to basically run everything that is in your R script, you hit the source button and it runs everything. If you just want to run the code line by line, or you select a certain part of the code, then you can hit actually the run button, and then it will only run the selected part of the code. Here on the right hand side, again, you can organize the different project files and they will open up in the editor in the top left. If you go to Tools, Global Options, that's where the main settings are to change the behavior of RStudio. One thing I like to do is to enable dark mode. This theme here is called Idle Fingers, and it's a little bit easier on the eyes when you work late at night. Again, also from within RStudio, or if you just Google it, you can find cheat sheets that help you interact with RStudio. Okay, that brings us to using base R. And first of all, let me mention some pitfalls of using copy and paste to run code. You see, two examples here actually cause trouble. The first one, you can see on the top, and let me actually highlight that, these inverted commas here are curly as opposed to flat. And so these curly inverted commas, they will not work. They will not be interpreted as were inverted commas by the R console. So if you copy this line, this will actually cause an error. The same with these backticks. They're also not proper inverted commas. So you either need single or double inverted commas to actually run this example. So what does this command do? It actually opens up a vignette on programming. So a vignette that's called programming. And because programming is a string, it's actually marked by these inverted commas. And you need to have, again, the right ones, right? The straight ones, either single or double, but not the curly ones and not the backticks. Yeah, but sometimes these inverted commas get messed up. So even if you have the right inverted commas in your clipboard, and then you paste them into PowerPoint or Word, and you copy that again, and then paste it back into the console, sometimes it gets messed up in the process because automatically PowerPoint may actually turn these straight inverted commas into curly ones. Yeah, so the single or double ones are actually for entering strings. The backtick has another specific purpose for some Tidyverse functions in particular, and we may actually learn about that a little bit later. And the curly ones don't really work for anything in R. Okay, that brings us to the R console, and I have some screenshots here on the right hand side, and I want to tell you a little bit about it. So again, R can be a calculator. So actually, as you interact with this recording, I would recommend that you also open up R and RStudio, and maybe that you pause this video to recreate some of those things if they're not intuitive to you right away, and see if you can replicate them, if they make sense to you. So R is a calculator. If you type 1 plus 2, it will show you an output that says 3. You can also define variables and then work with them. So in that example on the right hand side, I've defined A to be 2 and B to be 3, and then I can multiply A times B and I get the corresponding result. You always see the larger than operator here, and that symbol means the command you typed in begins here, right? So like every console or terminal has this. There's a symbol in front of your actual command that just says, okay, that's where you can type in your command. And then if you look at the output, there's actually the braces around the 1. And that has to do with R's conceptualization of things. So for R, everything is fundamentally a vector. So even a matrix is really a vector to R. It just assumes, hey, if you have a matrix, let's just store all the numbers within the matrix in a vector, and then at the end of it, have something that actually tells us, hey, this is actually representing a matrix. And so fundamentally, everything's represented as a vector within R. So if you have a scalar, so a single number, well, that's a vector of length 1. And so here, when you see in these braces the 1, it's basically says, okay, after this, you see the first element of this vector. And then, in fact, there's just one single element because it's really just representing a scalar, a single value. So on the top right-hand side of your RStudio, you have the history, and that tracks your input. So whatever I've typed in, it will actually track there. However, the history is not automatically saved. You can save it, but it's not automatically done. Other things to know, well, you can use the hash to comment part of a line or an entire line. And so basically everything behind the hash will be commented out. What does commented out mean? It means that it's not run. So here in this example, I've commented out b equals 10. And then as I call on b, well, it actually doesn't find b because this line b equals 10 has not been executed. You can use the stop button on the top of the console to cancel a command. You don't see that stop button appear unless you have a command running that is actually still running. So a lot of these simple commands that we type in here, they don't take enough time for you to actually realize that the stop button appears. But if you do something that takes a lot of time, this stop button will appear. Right, time for the first more interactive element here. So it's a good idea after this instruction to pause the video, to replicate that, and see if you can get the right answer. And then you get back to the video to see if you got the right answer. So type the following command into the console. 1:17. What does it do? What do you see in the output? Then type str, open parentheses, iris, don't close the parentheses yet, then press return. What happens? What do you see on the console? And then type a right parenthesis and press return. What is happening? Okay, so pause the video here, do that, and then get back to the video. Right, so you see 1:17 gives you all the numbers from 1 through 17. str iris, if you don't close the parentheses, you actually see a plus appear on the next line. So that gives you an opportunity to actually complete the instruction, the command. And then the command is completed and you see the structure of the object called iris, which in fact is a dataset that's called iris that has 5 variables and 150 observations. So when you work with the editor, actually RStudio helps you quite a bit. So once you type like the left parenthesis, it actually closes the parenthesis right away so that you don't make that mistake of not closing the parentheses. Code completion, right? So as I already said, the parentheses will automatically be added in RStudio as you work with it. If you hit the tab button, it actually suggests autocomplete options, including the arguments of the function. So you can actually see what the arguments of a function are. I get into more detail of the arguments of a function in a little bit, but it shows you those arguments, and then you can, if you press return, it puts in the name, and then you can pass things to those arguments right away. Storing objects. So I've used the equal sign before, but actually the proper way of assigning is to use the arrow. So the smaller than and the minus together. Actually, if you hit the Alt button and then the minus, it will actually do that for you. That may make typing a little bit easier. So that's the proper assignment operator to store objects as variables. You could also use equal, and I often do, I have to admit. But then as I share code and want to make it readable for others, I use the proper assignment operator, because that's what conforms to the style guide. And again, it kind of makes sense to follow those style conventions. Yeah, once you enter the variable name, it will actually display its contents on the console itself. So that's what you see here. Assigned 6 to y, kind of the improper way here. Once you type in y, you see its contents. Here it's done the proper way with the proper assignment operator. So storing objects. Variables appear in the environment pane after you made an assignment. So you have assigned a, b, x, and y, and you see those contents in the environment tab in RStudio. There are certain restrictions on what a variable name actually can look like. It needs to begin with a letter. It cannot begin with a number. It must only contain letters, digits, periods, and underscores. And I kind of recommend using underscores. They're kind of readable and allow you to have very telling variable names. There are certain reserved words like true, and you cannot assign anything to true because it's reserved. However, constants such as pi can be overwritten, but please don't. Well, think about a coherent naming scheme as you actually work on a larger project and you develop functions, or you work on the data analysis, because that will help you and again your future self and others to actually understand what you're trying to achieve by actually setting up these different variables. Again, make proper use of underscores, right, of snake case, to have very clear variable names. More in storing objects. So when assigning a string, you need to put it into into inverted commas, but actually not those ones. It actually messed them up for me as I was creating this slide. You have to use a proper straight inverted commas. Again, either single or double inverted commas. Like in Linux, R is case sensitive. You can use ls and rm. So ls will list all the objects in memory. So basically shows you the same thing that you see in the environment pane of RStudio. And rm lets you remove objects. So then the command rm list equal ls will actually remove all of the objects in memory. So how does it do that? Ls first pulls a list of all the objects that are in memory, and then you pass this list of objects to the list argument of the rm, of the remove command. So it will first execute this ls to get that list, pass it to the rm function, and that will then proceed to remove all of those objects. Yeah, R lets you reassign objects without any warning, and even between different data types. So if you have something that's a numeric at some point, so it's just a number, and then you assign like a character to it later on, it will not produce a warning. It will just reassign that object. Okay, time for another practice to work with. So please create a vector of integers ranging from 1 to 50. Call it integer vector 50. Then use the function C, that's short for concatenate, to create separate two-element vector of 0 and 1. So just a vector of length 2 containing 0 and then 1. Call that vector logical vector 2. Once you've done so, multiply those two vectors and then think about what happens. So actually do that, pause the video, think about this, and then resume the video to see what the answer is. So this is how you set this up. 1:50 actually creates this sequence from 1 to 50. Then we create the binary vector, and when we multiply it, you see that every other element, starting with the first one, is 0. So what is actually happening here? So in fact, before this multiplication here is conducted, actually R recycles this shorter vector. So it figures, hey, this vector of length 2, if I repeat that 25 times and make it 0, 1, 0, 1, 0, 1, 0, 1, it can actually match the length of the first vector with 50 elements. So I will do that first and then multiply those two vectors. Right? So you get an element-wise product after recycling the shorter vector so that the dimensions match. The interesting thing is you do not get a warning, and you also don't get an error from R. Other software may actually give you an error message, or at least a warning, but R does not. So you need to know that this is standard behavior in R. So what happens if there's sort of a mismatch and you can't really make them match? Well, then you get a warning message that tells you, hey, the longer object is not a multiple of the shorter object. It will still give you a result, right? It will recycle the shorter vector as often as possible. But again, the last one element cannot be applied in the replication of the shorter vector. So what's interesting here is you get a warning. You do not get an error. So it doesn't prevent you from actually getting this result, right? Because it's just a warning. So again, you have to know that this is the default behavior in R. And you have to, like, if you see that warning message is part of a longer function that you've written, that's a likely explanation where it comes from. A mismatch in the dimensions of the vectors that you're trying to get an element-wise multiplication for. Now let's take a look at functions. Type the function name and enter the values in the parentheses. Data passed into a function is called the function's argument. Also note that arguments can take more than just data. Arguments could also be functions or something else, but for most practical purposes right now, you typically pass in data or settings or configurations, anything that you want the function to know to those arguments. Yeah. See, on the right hand side, we have a very simple example. We have a function called round. So that basically rounds numbers, and it rounds 10.457 to 11. So by default, it seems to round to actually whole numbers. I can actually see that round also has another argument that's called digits. And if you set that to 1, it rounds the number to 10.5. So digits, the digit argument, tells round to how many digits it is supposed to round. It seems to default to 0. So arguments can have default values that if you don't specify the argument, it falls back to the default value. You can check the documentation of a function to find out what the arguments are and if there are any defaults for each of those arguments. Also, arguments can be the result of another function, and that's when you see basically functions inside function calls inside an argument. So let's say we wanted to round random numbers from a normal distribution. So then we basically first run rnorm10, which creates 10 standard normal distributed random numbers. And then if you wanted to round them with one digit, around this rnorm10 command, we put the parentheses and the round command call. So basically you have to read from the inside on. Right? So first we generate 10 random numbers and then we round them to one digit. We will later on see that in the Tidyverse world we have a different way of chaining functions together, and there we would actually first type the rnorm10 command, then have another operator that passes this to the round function, which will be a little bit more readable. But the default way of using this, of interacting with these functions, is to actually stack them inside one another. Okay, so we use the equal sign to specify names of arguments. So you can actually pass data to arguments by name, and that is the safest way to do it. If you don't do that, well, there's an order of arguments to be used. So the round function first takes in the number or the vector that you want to round, and then the number of digits you want to use. Right? And so that's what you see here. So we say round 10457, comma 1. So it actually takes this number 10457 and then rounds it to one digit. We are not specifying the name of those arguments here. And so you really have to know what the sequence, what the order of those arguments is. And so it's not quite as fail-safe as actually calling on these arguments by name. So that I think is generally recommended to do. Again, also some arguments are optional, other arguments are not optional, and you need to define them. So if you use named arguments, so you need to specify those names correctly. So in using this rnorm function, I'm calling it n equals 10, for I want 10 random numbers, that's correct. And then I define average equals 2. But the rnorm function does not have an argument that's called average. And then in fact we get an error, not just a warning, we get an error, so it doesn't execute that command because average is not the right argument to be used with the rnorm function. If you want to know what the arguments are, you can use the args command. So if you type args rnorm, it tells you, okay, it's function n, mean equals 0, sd equals 1. So actually the mean defaults to 0 and the standard deviation defaults to 1. So by default, rnorm gives you standard normal distributed random numbers, and actually n is a quantity of that. So if you don't specify arguments by name, it will be actually specified by order. So you can call rnorm 10 to 10, and so 10 will be passed to n, 2 to mean, and 10 will be again passed to the standard deviation. I think again it's a little bit more risky to not use names and just to rely on sequence. So let's say somebody else developed a function, they changed the order accidentally, and then the results that you would get by calling that function later on would actually be wrong. Okay, help. So if you need help with a function, you can actually call help. Help sqrt shows you the help for the square root function, or question mark sqrt that will also show you the help. If you want examples for a function, use the example function. Example, in parentheses sqrt, shows examples for the square root function. If you want to search the help documentation for just something you want to do, but you forgot what the function name is, you use double question marks to search for it. If you still need more help, there is Google, but you can go on Stack Overflow, which is a great resource, a great forum for programming related questions. However, keep in mind, it's not a platform to get help with your homework, right? And in fact, people will hate you if you do so. Also make sure you use the search function. That's another thing people on Stack Overflow don't like if you ask a question that has already been answered. If you have RStudio or Tidyverse related questions, RStudio also has a community forum that you can use. Okay, now practice again. Look at the documentation for the quantile function. Find out what the quantile function is about. Then find out what the nr.rm argument does. Right? What does it do? And also think about how you actually find that out. Once you figured that out, you use a quantile function to find the 25th and 75th percentile of the integers 1 through 150. So you generate integers from 1 to 150 and then run the quantile function on it to find the 25th and 75th percentile. Okay, again, pause if you need to. Do that before you resume the video to see what the answer is. Alright, the answer. And so, actually, if you just type quantile into your editor and then you hit tab, you actually get a lot of tooltips from RStudio itself. But of course, you can just type $quantile to actually open up the help and learn more about the quantile function itself. So then you see that it's fairly easy. 1:150 generates integers from 1 to 150. And so you pass that to the quantile function, to the first argument x, which takes in the numbers. And then props, right? So the argument props controls which quantile you want. And we pass actually a vector with 2 elements to it. And the elements are 0.25 and 0.75. So that will give us a 25th and 75th percent quantile. Right, scripts. So makes sense to always place code in a script to save for later use and to edit, to bug fix, to add something. In order to create a new script, again, you go to File, New File, RScript. Different ways to run code in a script. Clicking the Run button, again, is one way to do it. You can click on Source to run everything, but I typically use Control and Return or Control and Enter to run the code line by line or to run a highlighted area of a code. Working directory. So the getwd command shows you what working directory you're in. And if you want to read in, let's say, a CSV file, it's fairly straightforward to read in anything that's in your working directory because you don't need to specify the entire folder where the file is located. We will later on see that if you work with projects, then actually the working directory will be automatically set to the project directory. Otherwise, I think we usually default to like your home directory, so something like users documents. So, more about packages. Everything we've discussed so far was basically base R, and so we don't really need additional functionalities. But you may actually want to install additional packages. So how do we install packages? I've already shown you that in talking about the preparation for class, that you can use the install packages command. If you want to just install one package, it's just install packages, parentheses, and then in inverted commas you put in the package name. If you want to install multiple packages at the same time, then use C to actually stack together like a vector of different strings that contain the packet names. And again, here PowerPoint messed up again my inverted commas to curly ones. That actually won't work. If you want to install from Bioconductor, you have to first install like the Bioconductor installer. But again, we won't need Bioconductor for this class. If you install from GitHub, you need to install DevTools first, which is a package that helps you to install from sources like GitHub or actually Bitbucket. And then with DevTools install GitHub, you can then install packages from GitHub. So here you actually see how most people use it. Most people don't load the DevTools package. They just run the install GitHub function from it. So how do you use a function from a package without actually loading the package? Well, you see you use a double colon. So here it says DevTools : install GitHub. So this actually tells you need to actually look up the functions inside the DevTools package, find the install GitHub function, and then run that. without actually loading the entire package. You will also later on see that this colon operator is quite useful when two packages have the same function name, but those functions actually do something different. Then it makes sense to explicitly say which package you want to refer to. Oh, and you can also use a package manager. I like Pacman, the package manager, and you can just install it and then load it with pload. And what's kind of nice about Pacman is when you use the pload command, it will load the package if it's there. If the package is not installed yet, it will automatically install it and then load it. So that can save you a little bit of time, especially when you interact with colleagues and you're using different packages that you might not have installed. All right, very quick drill here. Try to install a package that's called NYC Flights 13. It's a very light package, so it should be pretty fast. Okay, install packages NYC Flights 13. Pretty easy. So what then? What do you do once you've installed a package? Well, probably you don't install a package just, well, out of nothing. Well, except for a class when you're being told to just install a package for exercise. But typically you come from Google or somewhere else. You look for a specific problem that you're trying to solve, and then a certain package is recommended. And at that point, you've probably learned a little bit about the package already. So installing the package itself will just copy it to your hard drive and make it available. You have to first load the package to actually use it. And again, you only need to install the package once, and then you can always load it when you need it. And then again, you can use the help functions like the question mark to learn more about functions within a package, or you can read the package documentation to learn more about what it's actually doing. So again, we're going to work a lot more with Tidyverse later on. So how do you load the Tidyverse? You actually use the library command. Library will, in fact, load a package. You could also use the require command, but it's only meant to be used within other functions. Okay, you can use a function from a package without loading it, as I said, with a colon operator. And so here, this will run the str detect function from the string R packet without loading the string R packet. If you want details regarding the content of a package, you can use, again, the help function and pass the package that you want to learn about to the package argument. So if you want to learn more about the tidyr package, you pass tidyr to the package argument of the help function. You can also look for vignettes. Vignettes, I do recommend looking at vignettes. They're often easier to digest than the full documentation, because vignettes provide you with an example using sort of the key functions of a package. So when you load a package like Tidyverse, it will actually display warnings sometimes, and here it will actually show you conflicts. So in fact, the function called filter is a function that exists within the dplyr package, which is part of the Tidyverse that you're loading here. But the filter function is a function that's already part of base R in the stats package. So now that we've loaded the Tidyverse, when you call on filter, it will actually always refer to dplyr's filter function. That's probably what you want after loading the Tidyverse. However, you may still want to use the filter function from the stats package for some particular application. So how do you work with that? Again, use a double colon to actually tell R which one you mean. So if you call stats : filter, you will use the filter function from the stats package. So sometimes it makes sense to be very specific on which function you actually mean, and to specify that with a package name. And in fact, if you want to really error-proof your code, that makes some sense. It makes it a bit harder to read the code, but in particular when you have a sort of a non-unique name of a function, it makes sense to be explicit about it. Now let's learn a little bit more about objects in R. So again, by default, everything's a vector in R. And in fact, everything's a vector to R, but it can be a vector with a lot of complicated attributes to represent maybe more complex structures, such as arrays. So what are atomic vectors? So those are just one-dimensional vectors that have a single data type, right? It's not a mix of numerics and characters, but it's one single data type. That's an atomic vector. And so that's the most simple data structure that we have in R. You can use the isVector function to test if an object is actually an atomic vector. So here you see that my vector is an atomic vector. It's actually a binary one, because it contains true, false, false, true. So it's a single data structure that's logical or Boolean, so true, false statements, and it has 4 elements. And when we run isVector of this my vector, it actually tells us true. Yeah, so this is an atomic vector. So what are the common atomic vector types that we have? So they can be logical, integer, double, or character. And integer and double are both like numeric types, and character is obviously not numeric, but it's also an atomic vector. So some R functions refer to doubles as numerics, and that's just like whoever writes the documentation there. So you can use is dot logical or is dot integer, is dot double, is dot character to determine if a particular atomic vector has that certain data type. Okay, let's create some vectors. So let's create a character vector and call it character vector. So we use character vector as sign symbol, and then we concatenate foo, bar, hello, and world. And again, each of those strings needs to be within like inverted commas. So let's create a numeric vector, and there's actually many operators that let you create numeric vectors. And before we already created integer vectors with a colon sign. We can actually use the seq, so the sequence command, to create a sequence from 1 to 42 in increments of 2. So let's create an integer vector, and if you want to use it, use the C, the concatenate function. You need to add a little bit. You need to actually add an L. So you need to write C, 1L, comma 2L, comma 3L. And that will tell this C function, hey, I need to create an integer vector. If you don't do that, it will actually default to a double, right? And it's kind of a waste of memory to save whole numbers, 1, 2, and 3, into a double, right, with just double machine precision, when in fact you know that those are integers. Yeah, and then logicals, you can create logical vectors using T and F, or true and false, but it's obviously better to use true and false, because true and false are protected by R, and T and F are not. So somebody could actually assign something to T, and then it would mess up this way of creating this logical vector. So if you want to examine a vector, you can examine certain properties of it. So you can use a length function to find the number of elements that a vector has. You can use typeof in class to identify its type in class. The difference between type and class is it's a little bit hard to explain in R, but actually if you run it, it's quite, it actually makes sense. So we have created this numeric vector before. So with length, we can obtain its length. So there are 21 elements in it. With typeof, we see, okay, the type is a double, right? And the class is a numeric. And as I've shown you before, the different classifications of atomic vectors, I could see that, okay, a double is a type of a numeric, and the integer is another type of a numeric. Okay, so str is a very, very versatile function that examines the structure of an object, and actually it can examine the structure not just of atomic vectors, but also of matrices and functions. And so if you apply that to this vector, to this atomic numeric vector here, then we see, okay, it's a vector that has a length of 21, and it's numeric, and you actually see an example of the first few elements of this numeric vector. So SDR is a very efficient way of examining what's inside a particular object. Okay, another practice round here. Look at the documentation for the RUnif function. Find out what it does. Well, kind of the next part of the question gives it away. Please create a vector with 75 observations that comes from a uniform distribution with a minimum value of -3 and a maximum value of 14. Don't forget to assign this vector to a variable. You pick the name. Okay, do that, and then once you've done that, write functions to examine this vector. Is this an atomic vector? kind of vector is it, and how long is the vector. So think about how you would actually assess that to double check that you've created the right thing. And now for the solution. So first of all, looking at the documentation, there are different ways. You can again use question mark RUnif or help RUnif. If you just want to see the arguments, you can use the args function to figure that out. So then we want to create the vector of length 75 that comes from a uniform distribution ranging from -3 to 14. So the argument names are n, min, and max. So n equals 75, min equals -3, max equals 14. And that will give us that RUnif vector. So that's the name that I chose. So then in order to examine the vector, you can run isVector to figure out if it's a vector, type of to get its type, and length to get its length. So now let's talk about attributes. So attributes are information you can attach to an R object, just like meta information. Attributes will not appear when you display an object, or it does not affect the object's values, but it's attached to it, and it can sometimes help to understand what the different values are, or what respondent or unit they belong to. If you want to check for attributes of an object, then you use the attributes function. So let's create just a quick text vector, call it text vector. And again, we concatenate just two elements here, hello and how's it going? And then if you check its attributes, we find that it's empty, so it's null. Right? So there are no attributes attached to the text vector. So there's a specific type of an attribute that's called names. So each element of a vector can have a name, just to further describe what it's about. And you can access that particular attribute with a function called names, right? So so you can either use attributes to access the attributes and then actually access the names attribute, or you can use a names function directly. And so that's what's demonstrated here on the right hand side. So in fact, you can assign new or change existing names by passing a vector of names to the attributes. Okay, so let's work with the text vector. So again, the text vector just contained, let me go back, hello and how is it going. So what would be appropriate meta information to describe hello and how's it going? So this is a greeting and this is a question. It's not really a question, but let's call it a question. So when we use names text vector, we see that it's also null, which is no surprise because its attributes also are empty. So now we can say names text vector and then assign to it a vector that contains greeting and question. So this will assign the names greeting and question to the text vector. So once we've done so and we check what the attributes of text vector are, we actually get its names, greeting and question. So actually when you call attributes text vector, you see that it says here $names. So in fact the attributes of a vector, that's actually a list, and the elements of a list are addressed with this dollar operator. So the list of attributes only contains one element, the element names, and that is a vector with two elements, greeting and question. So if you want to remove those names again, then we can again call names text vector and then assign null to it, which will then actually remove those names. So then if you again call names text vector, we see that it's null. If you call attributes text vector again, we see that it's also null. And the same, obviously, if you say attributes text vector $names, it's also null. We can do this exercise in a slightly different way. So we can call attributes text vector $names to specifically address that element of the attributes list called names, and then assign greetings and question to it. And that will do the same thing. Its names will then be greeting and question. Okay, so another important thing to know about R is coercion or typecasting. So when you combine different data types or want to force functions on certain data types, that can actually result in this coercion. And that always follows a certain procedure. So let's say you have a logical vector. So you have a vector that contains true and false and true and false. Then, and you want to multiply it, let's say with something numeric, then this needs to be made compatible. And it's kind of easy to do that. You just convert every false to a 0, every true to a 1, and then treat it as a numeric vector. If you combine something numeric with something character, well, then you can actually convert the 1 to a character 1 and a 2 to a character 2. So let me show you some examples to make this a little bit more clear. So 42 by default would be a numeric. But if you call s character, it actually turns into a character. So how can you tell that it's a character? Well, you actually have these inverted commas around it. When you convert a 0 to a logical with s logical, then it becomes a false. If you convert to a logical 1, it becomes a true. And if you turn into a numeric, a true, it becomes a 1. So following the conversion as I've just shown you on the previous figure. So we also see that there's automatic typecasting in R, and it's meant to make your life easier, but it's sometimes also dangerous when in fact it's somewhat unintentional and you may not even get a warning about it, and then you might be bug fixing for a while. So if you know that this behavior is a default in R, it actually helps you. Okay, so let's create a logical vector with 3 elements, true, true, and false. So if you call the sum function, so you sum up something that is Boolean or logical, now that's kind of strange, right? So it automatically converts it first, so it converts the trues to 1s and the false to a 0, and then takes a sum. So the sum of the logical vector will be 2, so there are 2 true elements in the logical vector. And that's very convenient, right? So when you have a logical vector and want to know how many truths there are, then you can just use the sum function. But along the way, it actually typecasts it to numeric. And the same happens with the mean function. So you would actually get the proportion of elements that are true. So what happens when you mix different types? So when you see the type of a vector 1 and 2 is a double. So as I said before, if you want it to be an integer, it would need to be 1L and 2L. But yeah, okay, so here we have a vector of type double with elements 1 and 2. But let's say we add another element to this vector that's actually a logical, so true. Then you see that the type actually remains a double because the true is automatically converted into a 1. And if you combine the 1 and the 2 with a string, so with foo in this case, then actually the entire vector is a character. So the 1 and the 2 will also be stored as character, not as a number. And so that is the standard typecasting or coercion behavior in R. Okay, so let's take a look at matrices. Of course, a matrix is a two-dimensional array. A matrix in R typically, well, always actually contains numeric data only, right? So you can't use it for something else, and you can't mix different types like integers and doubles. That's not possible. So you can use a matrix function to create a matrix, and of course you can also look up the help file for the matrix function. So in fact, that's a quick exercise for now. Look at the documentation for the matrix function. Then create a 5x4 matrix containing integers from 1 to 20 and filling it by rows, not by columns. Save that matrix as a variable called example matrix. Then examine the names, class, and dimensions of this matrix. So again, good point to pause the video again and solve that exercise. So let's take a look at the solution. So how do you get the documentation? Well, question mark matrix. Then create the matrix. Example matrix, a sign symbol, matrix, and then let's take a look at the arguments of this function. Data are 1 through 20, so 1:20. Nrow and ncol define the number of rows and columns, And then by row is the argument that tells the matrix function whether you want to fill the matrix row-wise or column-wise. By default, by row is false. So if, by default, it fills column-wise. I told you to fill it row-wise. So that's why the by row argument needs to be true. So then how do you examine the attributes? So you can examine names, that's null. You can look at the class, that's a matrix array, and the type. And in this case, that's integer, because we filled this with integers. And with dim, you can actually get the dimensions of that matrix, so 5 by 4. Okay, the next very important type is a list. That's a one-dimensional thing in R. So I know other languages may actually have something that's more like a field, so like a two-dimensional list. This is a one-dimensional list. So a list is super versatile though. So a list can just have a large number of elements, and each element can be something else. So each element can be a vector, a matrix, a data frame, and they all can be something different. And so the list function can be used to create a list, and you'll see it frequently used with models. Because if you think about a regression model, there's a lot of different things you would want to save about a regression model, and they all have different dimensions. So maybe a vector of the residuals, maybe some summary statistics, maybe the fit statistics, and they all have different dimensions and different types. So it's again very versatile. It's also a versatile thing if you want to pass information and settings and data to a function. So here, this example creates a list that has a couple of different things. So it has integers with a sequence command. It has letters, and it has a matrix as its elements. And you see the elements of a list, they have double braces. Right? So the first element is in double braces 1, the second one in double braces 2, the third one in double braces 3. And so you see that this first element here, that's just a vector with integers. The second one is a vector with letters, so characters. And the last one, you see there's a matrix in there. And then there's a data frame, and the data frame is really just a two-dimensional version of a list. So in fact, a data frame really just is a list with certain special attributes that make it behave like a data frame. So a little bit like a spreadsheet. So the data frame is most like a spreadsheet if you think about it. So what is it really? It's a named list of vectors with specific attributes. So each column is basically a vector, and again, they can be different types. So they can be numerics and character and so on. And they just all stack together so that they must have the same length, right? Because it's not a ragged structure, but each element of the data frame, each vector in the data frame, each column needs to be the same length. Okay, so how do you create a data frame? So you use a data frame function to do that. Data frames have a special class attached to it, and that tells R how to actually deal with a data frame. You can again use the str function to examine the structure of a data frame. So let's create a data frame that really uses different types of vectors in its columns. So here we have 3 columns with data. We have an ID. That's an integer. So our data frame will have 4 rows. So we will have 4 IDs from 1 through 4. Then we have a column that we call standard normal value. So we just create 4 standard normal values that we put into that column. And then we have another column that's called binary info, and that contains 4 binaries, so true, false. We can then control more things, so additional information for this data frame. So we can assign row names to this data set here. So we will actually assign names A, B, C, D to the different rows. So again, keep in mind, this is just like meta information. This is not actual data that you'd work with. This is just information that names each of the rows of the data frame. And then the strings as factors argument controls whether strings are automatically converted to factors. And that can sometimes be useful. We will see the string as factors issue I think several times over this class. And so basically what this is about is, let's say you have colors, and let's say in a column you have red and blue and red and blue. You could actually represent it as a factor. And so then maybe 1 would be mapped to red and 2 would be mapped to blue. And it's obviously cheaper memory-wise to save 1, 2, 1, 2 instead of red, blue, red, blue. And then you just need a mapping information to say, okay, 1 means red and 2 means blue. And that's what a factor would do. So if string as factors is set to true, R will automatically convert those characters to factors. If it's false, it will not convert it. Okay, so the environment tab in RStudio shows you the objects that you've loaded into memory or that you've created, so all the data, values, and functions that you have. And so the observations are in the different rows, and the different variables are stored in the different columns. Each of those columns could have a different data type, and so the data type could be numeric, integer, character, factor, or logical. And again, it could be different for each of the columns of a data frame. You can also find vectors there, or matrices, or arrays. So those are just like the arrays of different dimensions. And you could also find lists there. Again, lists are very versatile. So they're just like one-dimensional lists, but like each of the list elements can contain any type of object. So it could contain matrices or vectors and so on. And there could also be functions. So if you've defined your own function, or if you've run a script that defines a function, you would see the function also pop up there. So how do you import data? So by default, you would use the read.csv function to read in CSV files. There are other read functions for different file formats. And one tricky thing to know right now is, so before R version 4, the default was that anything that's string, so any column that contains like characters or words, they would automatically be converted to factors. And again, as I said, that's a little bit more efficient for storage purposes, and often also for analysis purposes. So when you have something like a color or a taste or something where you just have a set of categories, like a nominal variable, you probably want to treat it as a factor. But then sometimes maybe not. So really there's the question, okay, what should the default be? Should like a column that contains strings automatically be converted into a factor or not? And so that behavior changed. So starting from R version 4, the string as factors argument is actually set to false. So by default, anything that's characters stays characters, not turned into factor. And then there's also other packages to read in files, including CSV files. So the readr package from the Tidyverse does it as well. It's nicely integrated with RStudio if you use RStudio's data import function. It just adds certain conveniences. But read.csv works just fine, and I don't really see that many benefits from the read_csv for the most part. But CSV is probably not the best format for large data, and we look at other packages for accessing databases in one of the later classes. Then for exporting data, you would use a write.csv function to save it into a CSV file, and there's a row names argument that you can work with, so whether you want to actually write the row names into the CSV file or not. Okay, let's talk a little bit about style, because I already said that the Tidyverse developers, they had some style guides, and it actually makes sense to look at that. And so why is that? Well, very often you would work collaboratively on data analysis, or again, you would share it, you would archive it, and maybe look at it later on. And again, your future self is often very confused when you don't have well-documented code. So it makes sense to think a little bit about the style guides. So just a very few quick examples here in terms of naming conventions. So, if you just name things script1, detail, it's not very telling. So instead it makes sense to be very explicit about what analysis are you actually doing, and again use sort of snake case, so these these underscores instead of spaces to prevent errors. But you know, the file name can be 255 characters long. So you know, use it. Have very telling names for your scripts. Again, underscores work well usually. If you just write everything together without any break or underscore or dot, that's probably not very clear. Also, try to structure your code. You know, when you use the hash sign, the hash character, I mean, it allows you to comment out code, and you can therefore use that to mark certain elements in your code and add like headers to different sections of the code. And there's also a built-in function. So if you hit Control Shift and R, it actually lets you type in sort of a header for a specific section of a code, and then actually RStudio shows you the structure and allows you to jump between these different sections of the code. And that's something you should probably use instead of just having you know, code after code in each line. Also, try to make the code itself more readable. So use spaces where appropriate, and just try to make it easy to the eye to catch the meaning of the expression that you're using. Now we're going to look at more essentials of data handling. The first of which is selecting values. So for most purposes, we're going to use the brackets to select values from a vector or a matrix or another object. And you can use a couple of techniques to actually select which values you want to select out of a vector. One nice thing is that R is really pretty flexible there. You don't have to select only like contiguous parts of a vector. So you're not forced to just select, let's say, the first 10 values of a vector or the last 10 values. You can pick out whatever element out of a vector you want. And so what can you use to do that? You can use integers, positive or negative. You can basically pick the IDs of the vectors that you want to pick, or you can basically deselect the elements of a vector you don't want to choose. You could create an empty vector as well. You can you know, use blank spaces. You can use logical values or true false statements. And you can also address by name. So if you have an attribute set on top of a vector, you can then use the name attribute to pick out different values from a vector. So let's actually start with a little bit of practice right away. Use the following commands down below to create a vector with 26 random values, actually coming from a random normal distribution. The setSeed command that we have here ensures that we all get the same random numbers, because in fact those are pseudo-random numbers, and if we initialize a random number generator with the same seed, we all get the same random numbers. And then rnorm again generates random numbers following a standard normal distribution, or in this case, actually not a standard normal distribution because it's mean 0, but it's standard deviation 5. So just run this part, and then I have some assignment for you. Run each of the following commands here one by one, and then try to figure out what they actually do. And this way we kind of learn by example. So pause the video, run those commands, figure out what they mean, and then look at me talking about the solution. Right, for the solution. So the first command here is just using empty brackets. And what does that do? That selects every element of my vector. Okay. And my vector containing the random normal distributed numbers. So if you want to run my vector in brackets 5, what does this do? Well, it returns the 5th value of my vector. What does my vector 3:7 do? Well, it selects the 3rd through 7th element. So the 3rd, 4th, 5th, 6th, and 7th element of my vector. Then we can use C to concatenate 1, 3, and 6, and that will pick the 1st, 3rd, and 6th element of my vector. Putting a minus ahead of 2 to 14 I will actually select every element of my vector except the 2nd through 14th element. Also be careful here, you really need these parentheses, because otherwise it would go from -2 to 14. That's not what you want. You actually want all of the numbers from 2 to 14 to have a negative sign attached to it, and that's why you need the parentheses. So my vector 0 returns an empty object. Why is that? Well, R is 1-based, not 0-based. Other programming languages are 0-based, so the 0th element of an object would actually be the first element. But R is 1-based, so the first element of a vector is indexed with 1. So then 0 just returns something that's empty. My vector C, true, false, false, returns the first element because it's attached to the true statement here. Then excludes the 2nd element, includes the 3rd element, and then doesn't include the 4th and 5th element. And also what you will notice is that R automatically recycles the vector here, so the selection vector with the true false statements to match the length of my vector. And we have seen this recycling at work in other examples before, right? So works the same way here. My vector C, B, and R, what does this do? So we actually have a vector of strings being B, N, and R, and that actually addresses by name. So if you actually go back to where we created my vector, you can see that we actually assigned names to each of the 26 elements. And I'm using letters, so that's also something that's inside R already. So that's a vector containing the 26 letters of the alphabet in lowercase, and we assigned that to the names attribute of my vector. So we can actually select elements of this vector using the names. So we are picking the element B, N, and R with their corresponding values. Okay. Let's focus a little bit more on selecting rows versus selecting columns. In the next exercise, we will practice the selection of rows and also some columns using one of those built-in data sets. So look at the documentation of the World Phones dataset that's built into R. Okay, a few hints. World Phones in brackets, comma, will return all rows and columns. So when you want to understand selecting rows versus columns, typically in rows we have observations and in columns we have different variables. The order of which is row, comma, column. So everything that is before the comma is actually indexing rows, everything after the comma is indexing columns. With that said, please extract the following. The first row and all columns from World Phones, the 2nd, 3rd, and 6th rows, and the 2nd through 5th column. Then select all rows, but repeat the 3rd column twice. Then select all rows, but every column except the 1st and the 7th. Then create an empty data frame, so think about an empty object, and then select the 2nd to last row. And use a function there. Don't just simply hardwire the 6th row, but like independent of how many rows this object has, always select the 2nd to last row with all columns selected. Okay, again, try that for yourself. Pause the video and then go back to it. So, selecting the first row in all columns. So that is World Phones 1, comma, because again, it's row, comma, column, the way that you select. So an interesting observation here, if you just run that, it will actually return a vector. Because R figures, hey, if I'm only selecting one row out of a data set, one dimension is actually enough to represent these values. Right? I don't need rows and columns to represent just one single row. So it automatically drops the unnecessary dimension from this and represents the result as a vector. And that is probably one design decision that some of the core R designers probably regret today, because that can cause a lot of trouble when you create your own function and you allow people to select, several rows of a data set, but then you also allow them to just select one row. And then in one instance, what happens is the object that is returned is a vector, and in other cases it's a matrix. For some operations that you want to do with that object, it probably matters whether it's a matrix or a vector, and then you can run into trouble. So if you want to prevent this drop of dimensions, you actually have to specifically tell R drop equals false as an extra argument to our bracket operator. So how can you tell that this is still a matrix? Well, you see the 1951 is still being displayed here, which is a row name. Obviously, that row name is lost when R drops the row dimension and simply represents the result as a vector. So that's one of the probably most quirkiest and weird things about R. So when you write a function, it will actually contain a lot of drop equals false statements because otherwise your code may run into trouble. Okay, now select the second, third, and sixth rows. Okay, so we concatenate 2, 3, and 6 for row selection, and then 2 through 5 for the columns. Selecting all rows, okay, that is nothing, comma, that is selecting all rows, but then for the columns, we just want to actually get the third column and get it twice, so 3, 3. Selecting all rows, again, empty comma, and then select all the columns except for the first and the seventh. So we concatenate 1 and 7 and sort of deselect the first and the seventh column. An empty data frame, well, if you index with 0, 0, you actually get an empty matrix of dimension 0 times 0. Selecting the second to last row programmatically, so you obtain the number of rows using the nRow function, so nRow world phones minus 1. So this will always select the second to last row, independent of how many rows are actually in the data frame called, or matrix called world phones. Okay, let's shift a little bit more towards selecting columns or selecting variables, especially in the data frame. And that's where they're typically stored. There are a couple of ways that you can index that. So you can, again, you course work with brackets, and that's like comma, column index. You can also in the data frame use an ID. So you can say, okay, I want to select the first column or the second column, the third column. So you can also index in that way. You can use the dollar operator to access named columns. And typically in the data frame, each column is named, and you can access that this way. And you can also use a double bracket operator to access list elements. Notice data frames are also lists, but they're a little bit of a special case. In a standard list, like the double bracket is sort of the proper way to access what is inside a list element. Well, Tidyverse and dplyr have more intuitive ways to do all of this, but again, we want to focus on base R for this lecture because it's stable. It will probably stay the same for the next 10 years, as opposed to the Tidyverse function, which may change, whenever Hadley and others feel like it. Okay, selecting columns. So one distinction between different methods is whether you preserve the structure or you allow the structure of what you're selecting to be simplified. So if you use the single bracket index to access elements from data frame, then you actually preserve the structure. So whatever you're selecting, even if you're selecting just one column from a data frame, the result will still be a data frame. Right? It's not dropped down to a vector, even though that simplification would be possible. If you want that simplification, so you're picking a vector out of a data frame and you want that to be a vector, not a data frame with just one column, then you have to use a double bracket operator. And one other thing that simplifies the structure is when you use the dollar. So the addressing by column name. That also drops down the result into a vector. So we can play with an empty cast dataset a little bit to try to understand the consequences of all of this. So selecting just with single brackets. So within the single brackets, we can address by name, so disp for displacement, or by ID, 3 for the third column. and both give us still a data frame showing all the row names, and then the single column showing the displacement of those cars. Let's actually verify that. So if we type str and then for our selection via name or via index, both actually yield a data frame with just one variable. If you use double brackets, then you can see that the structure is simplified because the output is just a vector. And you don't see the row names anymore because there are no row names to be assigned to the simplified structure being a vector. So let's verify that with str, and indeed you see it's a numeric vector with 32 elements. Selecting columns with a dollar sign. So the dollar only allows you to actually address by name. You cannot address columns by index, just by name. And that then also yields a vector, obviously. So now let's, that we've done the data frame, let's actually select values from a list. You can also use dollar to access named list elements, and that can sometimes be very useful. Single brackets, that will still return a list, and double brackets, that will actually just show you the inside of that particular list element that you're selecting. Sometimes you need a combination of those to get what you want. And also again, keep in mind that data frames are just like a special type of list, so some of these things would also apply to a data frame. All right, so let's practice that a little bit, and let's have a little bit more of an applied example. So the LM function in R fits a linear model, so standard multiple linear regression model. So let's actually fit one for that empty cars data set. And what we do here is we're explaining mpg miles per gallon tilde dot, and tilde dot actually tells this function to explain mpg with all of the other variables present in the data set. Using the data argument, we tell the LM function to basically use the columns within the empty cars data set. So the model output will be stored in an object called model. If you run the command str model, then you can examine this model object. Do that and actually look at it. And then I have a couple of commands here, and I just want you to play with that model output a little bit to understand how list indexing works. Okay, let's take a look at the answers or solution. So we fitted the model here, and typing in str model shows you, hey, this is a list with actually 12 elements. So there's a lot of model output associated with a standard linear regression model. And we have model coefficients, right? So there are 11, including the intercept, there are 11 explanatory variables or betas in this model. So we have a vector of length 11 containing the coefficients. Because we have 32 observations, we also have 32 residuals, right? And you see that it's a named vector. So for each residual, the name attribute carries the row name from the data set. So there's a lot more in there. And you see when you actually fit models, there's just different types of outputs, different lengths of vectors that need to be stored. And so the list is actually a pretty nice and versatile way to do that. So if you type model in brackets and then addressing the name fitted values, you actually see the predictions for each of those observations being returned. So if you do that with a single bracket operator, you see that the output is actually still a list. So it's a list with one element, and that one element is fitted values. If you use double brackets, then this would actually be a numeric class and would actually come down to being a vector. So if you want to look at the weight coefficient, so model.coefficients contains all the model coefficient. If you just want to know what the beta is for weight, then we can also address it by name. WT is a weight variable in this data set. So if you check the type of that, it's just a numeric, because it's just one single coefficient. It's actually a negative coefficient, which makes sense. The heavier the car, the lower the mileage. Looking at the residuals, so we access the element called residuals and just displaying the first 10 elements to make it more compact. If we actually check its type, it's a double. So again, it's just a simple vector of doubles showing the residuals of the first 10 observations. Okay, modifying values. Let's start with a very simple thing, changing values of a vector one at a time. So let's create some vector. Let's call it some vector and let it contain the values from 1 through 5. Then let's actually select an element to change. So we first need to tell R which element we want to change. Let's say we want to change the first element. So let's put 1 in brackets. That will select the first element. Now we can use the assignment symbol, so the arrow or the equal sign, and then put in another value. Let's just double check it worked, and it did. So that wasn't too hard. But we can also modify several values at the same time. So we could select the first and the third element and replace it with 99 and 999 respectively. If we want to change the remaining values to be -2, let's select them, elements 2, 4, and 5, and we can put in -2. I don't have to write C -2, -2, -2, because R will automatically recycle the -2 3 times to match the dimension of my selection. Let's just check this worked, and it did. How do you modify values in the data frame? Well, basically you just need to select the corresponding column that you want to change first. So we could take the iris dataset, create a copy of it. It's a flower dataset. So let's actually say we want to access the sepal length column. So we use a dollar operator to do that. Access the first 3 elements and then put in 1000. We could also replace those 3 values with individual corresponding values. Let's say 9, 99, and 999. Let's just check that the first command worked, and indeed it replaced the first 3 elements of sepal length with 1000. One other trick or useful tool for modifying values and selecting values is to use logic. Logic in R is actually pretty straightforward. So 1 does not equal 2, well, that returns true. If you type 1 does not equal 2, it returns true. So exclamation mark equal means not equal. So when we type 3 larger 513, it returns false, true, false, because 3 is not larger than 5, but it's larger than 1, and it's also not larger than 3, well, because it's equal 3. We can also compare like 2 vectors element-wise and look at 513 versus 315, and we see that it returns false, true, false. What's also really interesting is the in operator. So we can type 1 in 513 and it will test if 1 is in that sequence 513, and it is, right? So the second element of 513 is 1, so 1 is indeed part of 513. We can also do that for multiple elements. So we can check for 19 and 3 if they are part of 513, and that returns false, true, because 19 is not inside this, but 3 is. And we can test it for even more elements. We can test whether 1, 8, 0, and 9 is in 513, and we get the corresponding result. Now we can use logic to actually select and modify values within a data frame. So let's actually work with the iris dataset again and create a copy into RSDF first of all. Then, well, you can also look at the commands that I've put up here and think about it yourself and what it does, but I'm going to explain it here. So RSDF $petal width selects the petal width variable out of the dataset. Larger 1 means that we actually get a vector of logicals telling us for each of the cases whether the petal width is larger than 1. So then later on we can use it as a selection criterion to select those cases, only those flowers where the petal width is larger than 1. So if we want to have only the observations with petal width larger 1, we can simply use the brackets to select those elements. So let's say we only want to have the petal width for those cases that have a petal width larger 1. We can first of all select the petal width and then use the brackets to create that subset. We can also use that to modify this and actually type in -3, or maybe if we think that larger 1 is not a plausible value, we could also replace it with an NA, for instance. subset and select. That's basically what logic can help us do quite efficiently. So here we are selecting all the columns from the iris dataset where the sepal length is larger than 7.3. We can actually also combine several statements, so we can actually select based on multiple criteria at the same time. We can combine those statements using AND or. So we have the AND symbol and then the OR symbol to actually do that. So here we are selecting everything with a sepal length larger than 7.3 and a petal length larger than 6.3. So the AND sign actually combines that. This would select everything with a sepal length larger than 7.3 or a petal width that is less than 1.8. Oh, you can also combine several things to create also conjunctions and disjunctions. You should then use parentheses to actually combine elements where you want to have an AND relationship or an OR relationship. Also, one function that is not part of base R is not in. So sometimes you want to know for each element if it's not part of a certain sequence. So there's no function for it, but you can just define it yourself, either by just writing it as a function. Let's say we define %, exclamation mark in % as a function of x and y, where we turn the negation of the in operation between x and y. So second line is a more elegant way to actually write this. And then once you've defined that, you can actually use the % exclamation in % operator. Okay, let's practice modifying value. Read the documentation for the ETHOF built-in R dataset, then filter the dataset for certain observations. So where the tobacco consumption is either 0 to 9 grams per day or 10 to 19 grams per day, and the number of cases for that observation is greater than 0. So here you have to combine certain logical selectors. Think about it, pause the video, and then check if you got the right answer. Okay, so first of all, check the documentation with question mark, and then how do you pull that information? So we wanted to have two selections, and here a very elegant way to do that is using the in operator. So we want the tobacco consumption to be either 0 to 9 grams per day or between 10 and 19. Again, this variable here is basically a factor, and so we can then select both of these factor levels that were actually given in the instruction. And we can combine this selection with an n cases larger 0. We have a blank after the comma because we want to select all of the columns from the dataset. Well, now we're going to talk about missing data. In R, missing values are actually recorded as NA in capital letters. So that's also protected, and NA means missing value, not available value. Missing values prevent R from calculating sums, means, equality checks, and so on. And so you can see that here. If you just add 8 plus NA, well, it will return NA. Well, we have no idea what the sum would be because we have no idea what one of the elements of the sum is. It also prevents you from computing a mean. So if you use a mean function to compute the average of 1, 2, 3, NA, and 5, it also returns NA because we have no idea if this is a small or large value. We have no idea what the average should actually be. So you can use the is.na function to check for missing values, and so it's another logical operator, and so if you apply that to a vector or matrix, it will simply return true or false for each of those elements of the object, stating whether it's a missing value or not. And you can take the sum of that to count how many missing values you have. Oh, one more thing. So a lot of functions have this nr.rm argument, and that will automatically then remove missing values. By default, NRRM is set to false, right? So that you actually get the NA value as a result. And that's also a good protection, because you don't just want the software to remove missing values, then give you maybe a fantastic result, and you might not even realize that, hey, most of those values were maybe actually missing. So you have to be explicit about, no, I know that there might be a missing value in my data set, and I actually want them to be removed. So you specify nr.rm to be true. Not all functions use nr.rm as an argument consistently. Most of base R functions do, but if you use other packages, they may use different arguments to control how you want to deal with missing values. Counting missing values. As I already said, is_NA basically returns logicals, and you can then compute the sum of the missing values by simply summing up the result of that. Okay. So we have an example data frame here that I call df. There are 4 columns that I just name call 1 through call 4, and you see the first column has 3 numbers from 1 to 3, and then also a missing value. The second column also has a missing value, and actually the last column has 3 missing values, right? And the third column doesn't have any missing values. So when you use is.na, you actually see you actually get basically a matrix of logical statements. So you get false and true in here, indicating where you have a missing value. So if you compute the sum of that, you actually get the total number of missing values. So in this case, 5. Of course, it makes sense to use the callSums function to compute the number of missing values per column. So here we have a column-wise summary of the number of missing values. So that's how you'd assess the quality of a data set that you've received. And if there's a lot of missing values in a particular column, you'd probably investigate if there's a particular reason for that. So one way of dealing with incomplete observations is to basically remove those observations completely. To figure out how to mark those cases for removal, you can use the complete.cases function, and that basically gives you, you see here, true, false, false, false. It gives you an information about how many missing values you have per row. If that is actually more than 0, then it's going to return false, and if the number of missing value per case or per row is 0, then it returns true. So let's actually take a look at our data set again. You see that in the first row, we don't have any missing values. So all the elements are actually marked false. All of the other rows, and rows are observations, have at least one true result here, and that means they have at least one missing value. So only the first row, so only the first case is actually complete, and that's what the complete cases function shows you. You can also use the na.omit function to automatically remove any of these incomplete observations, and then you can feed that into your analysis right away. And of course you can do that, but probably want to have an initial data cleaning step where you actually keep track of how many cases you're about to remove. So how do you subset? Well, you could use a complete cases function, so then you would just use df in conjunction with braces to select just the first row. Or you can subset with the exclamation mark operator to retrieve the incomplete cases. So if you want to just select all the cases with missing information, maybe you want to do that to assess why the missing values exist, if there's something strange, if there's an interesting pattern here. And then again, if you use the na.omit function, you can simply obtain all of the observations that are complete. So in this case, that is just the first row of our data set. So be careful, discuss with the stakeholders of the data set what you're allowed to remove, what the reasons are for missing observations. Not all missing data is missing at random. If it's missing at random, it's safe to remove. If there's a pattern behind it, so it's not missing at random, then you have to be very careful, and maybe you need to do other things with your missing values. Maybe you want to impute values as a good guess, or maybe you want to explicitly deal with the fact that some observations, some cases have missing observations and others don't. Really depends. And again, that's something for your statistics class or critical thinking class to think about. All right, so in function missing value handling, some standard functions like mean and median, as I've already told you, have this nr.rm argument, and that controls how NAs are handled. And so that's probably a little bit more convenient than always using the na.omit function. So it's then basically equivalent to running na omit first and then running the mean function over it. Yeah? So, but again, not all functions have this na.rm argument. Okay, let's take a look at table, and we get back to table when we look at exploratory data analysis. So the table function creates frequency tables, and that's quite useful for non-numeric variables. So for factors, for logicals, for characters, for anything that you expect to be nominal or ordinal in terms of its scale level. By default, the table function excludes NA. And if you want to also get a count for the number of missing values, you have to tell table that with a particular argument. And that argument is called use NA. And you have to set that to always. And so if you do that, then the table function will give you also a count of the missing values. So again, here you see that you always need to check the arguments of a function and also check what the standard behavior is. Other pieces of software might actually default to always showing you the number of missing values in something that you summarize with a frequency table. Not so the table function in R. You actually need to tell it to display the missing values. Right, time to practice a little bit with missing data. So how many missing values are in the built-in data set called air quality? So air quality is one of the many built-in data sets for practice. How many missing values do you have in total? Which variables are the missing values concentrated in? So you need to look at the missing values by column, by variable. How would you impute the mean or median for these values? Right, so think about how would you compute the mean and median first of all for all of these variables, and then how would you put them back in? How would you replace those missing values? And how would you omit all rows containing missing values? Right, so just like 3 and 4 represent different ways of dealing with those missing values. Again, pause the video, think about it, do it on your own, and then resume the video. Okay, let's take a look at the answers. So how many missing values do we have? So simply sum is NA air quality. That will give us a total number of missing values. In this case, 44. Which variables have the most missing values? So we compute the column sum, so the column-wise sum of missing values in air quality. And here we actually see that within ozone we seem to have the most missing values. So to play more with this, let's actually save a copy of air quality dataset where you don't need to do that, but since air quality is built in, I'd just like to create a copy of it. Let's call it air quality copy. So then let's think about how to impute the mean and the median. Well, so there are 2 steps basically to think about. First of all, computing the mean or the median for those variables with missing values, and then actually putting it back in. So let's take a look at this command here. So there's basically 2 parts to it, right? So there's what we assign to, so everything to the left of the arrow, and then there is our computation of the replacement value, so everything to the right of the arrow. So let's first start with the left here. We want to do this variable by variable, starting with the ozone column where we have the most missing values. So we're selecting the ozone column with the dollar operator. That's one way of doing it. And then we use the brackets to actually select the missing values. And then we say, okay, is.na air quality, copy, and then dollar ozone. So this is NA, air quality ozone gives us a vector that actually picks the observations with missing values in the ozone column. So applying that with a bracket to air quality ozone selects those values that are missing. And then we need to say, okay, what to replace it with. And so that's where we compute the mean. So we compute the mean of air quality ozone, but of course we need to remove the missing values in order to compute the mean. Because our best guess for missing value would be the average observed value. So we need to remove the unobserved values here. And just to check that it worked, let's compute again the number of missing values by variable. And that's what I've done here. And you actually see that, okay, now ozone doesn't have any missing values anymore. And lastly, if you want to keep only the complete cases, two ways of doing that. You could first figure out the rows that contain complete cases with the complete cases function. So complete cases air quality gives us a vector of true and falses, stating which row contains complete cases. And then we can use the bracket to select the complete cases out of this. The more easy way is to simply use the na.omit function. Both lead to the same result. And then if you actually check our newly assigned air quality complete data set, we actually see that there are 0 missing values remaining. Now let's have a look at basic data exploration. And again, the Tidyverse will offer a lot more functions for very efficient and fancy data exploration, but we want to use the basic tools first to understand what's actually going on under the hood. So, in general, before you get into any modeling, you should conduct what's called exploratory data analysis, or EDA, just to know what's going on in your data. And for quick data exploration, we can just use some base R plotting functions or tables, and that's often enough to just get a very basic understanding, especially if the data set isn't all that big. We usually begin with a univariate analysis, and that means we look into each variable one at a time. Once we've done so and we suspect certain patterns to occur, we may turn to a bivariate analysis, where we check the relationship between any pair of variables that we might find interesting. And we do so with cross tables if two variables are categorical. We do so with correlations if two variables are numeric. And we can do subgroup analysis if we have a mix between numeric and categorical. We may also use some simple regression models, just using that LM function in R to find certain patterns in the data. And again, without imposing much structure, that just gives us an idea if there's a relationship between sets of variables. Just a reminder, again, this week, this session is about getting to know base R. It's not about using all the fancy packages. So table, as I've mentioned before, that creates a frequency table. It can also create a contingency table if you want to do bivariate analysis. So the same function does those two things. Here, we can look at the relationship between transmission and engine layout in the empty cast data set. So I think they have the V-shape engine layout and then another engine layout, and you can actually see if there's a relationship between that engine layout and the transmission type, whether it's automatic or manual. And so that's what I'm showing here. So it's a bivariate analysis between the transmission style and like the engine layout, whether it's V or not. And so this is the resulting contingency table that you get, showing you the absolute counts. Then on top of that, you can use the prop table function to show you either the row-wise percentages. So if you use comma 1, it shows you row-wise percentages, which means that rows will add up to 1. Or if you set that argument to 2, you get column-wise percentages, and so here the columns add up to 1. So that it depends whether you want to know the proportion of manual shifters for a V-shaped engine layout, or if you want to know the proportion of V-shaped layout for manual transmissions. And so that determines which way around you want to compute those percentages. And again, that's done with prop table. Then core lets you compute Pearson, Kendall, and Spearman correlation. By default, it will give you a Pearson correlation. That's probably what you want to use most of the time. So if you wanted to know the correlation between displacement and quarter mile time, we see that there's a negative correlation. So larger displacement leads to faster quarter mile time, which makes sense. And you can explicitly state the method should be Pearson, but that's what it defaults to. Then you can set that to Kendall or Spearman if you try to correlate ordinal variables. So then for subgroups, there are different ways of doing, averages or standard deviations by subgroup. You can use aggregate, by, or t-apply. And so they all sort of serve the same purpose. The outputs are going to be a little bit different, and the syntax for using each of those functions is also slightly different. So let's say we wanted to know displacement by the number of cylinders. We could subset manually and say, okay, let's actually take the displacement information, empty cast $disp. Then we use the brackets to select only those cars where cylinders is equal to 4. Then we do that with 6 and then with 8. And then each time we actually compute the mean of this subsetted vector. And so then we have these three values for average displacement by number of cylinders. And you can see as more cylinders, the average displacement also goes up. Okay, that makes sense. But is there a better way? I mean, with just 4, 6, and 8, it's kind of doable. If you have more different values for the number of cylinders, it gets a little bit tedious. So one way is to use aggregate, and personally I like to use aggregate function if I have to use base R the most. So the syntax works in this way. You write empty cast $disp. So that's the variable that you want to compute the mean for, and then you type in tilde empty cast cylinder. So it's disp tilde cylinder, right? So you want to split displacement by number of cylinders, and then you want to aggregate that using the mean function, and you have to be explicit about this argument fun for function and in capital letters, and then say that you want the mean. And what this will give you is a data frame where you will see the number of cylinders in the first column and then the averages for the displacement for each of those groups. And I personally like this output the best. I mean, that's kind of what you want. If you use a by function, you say, okay, by empty cast disp. So we want to, again, summarize the displacement. And then the second argument is what you want to apply this function by. And in this case, it's cylinders. And then which function you want to apply? You want to apply the mean. So here you get the same values. It's just that the output is not a data frame. And you could turn this into a vector where you have simply these three different averages. But I like this data frame output where I have in the data frame not only the average displacement numbers, but also the corresponding number of cylinders. And you could also use a tapply function to do the same thing. But it also, it gives you a named vector, and that's kind of nice. But I personally prefer aggregate. But you're free to use whatever you like. Okay, so that's what we've done. Again, I prefer aggregate, and if you want to try it out, you can copy and paste this command and replicate that for yourself. Okay, so then plots. So also looking at some visualizations is helpful, especially for numeric variables, where a correlation only shows you the strength of a linear relationship, but a plot can reveal any other type of pattern if you look at it. The plot function is sort of the most general function to generate a plot. It can create a scatter plot, like in this example, but it can also be used to plot a lot of other things. And in fact, the class of certain other objects defines how the plot function actually operates, and it tells the plot function how to create a corresponding plot or even several plots in a row. Yeah, so some base R plotting functions let you specify the data set without using the dollar to select the variables. That's also a very nice feature of those functions that makes the syntax a little bit easier to read. But I'm going to use a dollar operator in this example. So here we are actually showing the displacement against the quarter mile time in this empty cast data set. So it's simply plot empty cast disp, comma, empty cast qsec. So that creates a very basic scatter plot. Base R plots may not be pretty, but they're quick to make. Okay, let's practice. Use a WTS or chicken weights data set to make the following summaries. A table of the feed variable. Use the dollar symbol to select the feed variable here. Then a histogram of the weight variable. Again, you can use a help function to figure out what the function is called that creates a histogram. Then create box plots of the weight variable by feed. Look at the documentation for the data set, and then also for box plot if you need. And then also compute the average weight by feed. Again, pause the video, try to do that yourself, and then take a look at the solution. Okay, table of the feed variable. So you simply use a table function. Table, chick weights, dollar feed. That gives you the right answer. A histogram, well, in R, the function is called hist, and that gives you a histogram. So hist, chick weights, dollar weight gives you that histogram. Box plots. So here it's a group box plot. So we want to create a number of box plot of the weight variable split by feed, so by what the chicken were fed. So again, use the tilde operator here. So weight tilde feed. That's weight by feed. And here this function, the box plot function, lets you specify the data set with the argument called data. If you don't want to use that, you could write chick weights dollar weight tilde chick weights dollar feed. So both of these commands are equivalent. The first one is maybe a little bit more readable. All right. And then compute the average weight by feed. I'm using the aggregate function here, but you could also use the by function or the tapply function if you want. So here it would be aggregate chick weights dollar weight tilde chick weights dollar feed, and then fun equals mean, and then you have the corresponding means. So those means correspond to the means by group that you see in the box plots. But keep in mind those are box plots, so the middle line here is a median. You could also change this command here to median, and then it would give you the values of where exactly those middle lines are in those box plots. Okay, for your convenience, I've summarized some key functions on this table here, including help, get your working directory, arithmetic, assignment operator, listing and removing objects, installing packages, and looking at vignettes. For numerical summaries, checking dimensions, obtaining names, so the name attribute, obtaining the first few rows or last few rows to just take a peek at what the data is, assessing the structure of data, counting missing values, summary statistics, frequency and cross tables, and subgroup means. So that already helps you for some very basic exploration for dataset. And then some basic plot. So for the most part, it would be the plot function for scatter plot or line chart, then bar plot if you want to visualize like a frequency table, hist for histogram, and box plot for box plot. All right, in preparation for next week, read the assigned readings and complete the assigned homework.